Hi. Today we're doing a little bit of a new topic. We finished electricity, and so we are doing a small amount of chemistry before the summer holidays. And we're going to start off with the history of the atmosphere, and then we'll move on to things like global warming and climate change. So, this before we can do those things, we need to know what the atmosphere is. So, we're going to be able to describe the theory for the development of the Earth's atmosphere. Let's start off with some questions, though. Can you name 5 gas elements? Our gas at a room temperature. I suppose everything's gas if you heat it high and hot enough. 5 gas compounds. So these are not gases that are in the periodic table, but if you can think of some that are gases but compounds. 3 types of bonding. There are 3 types of bonding. Can you remember what they are? And then, which of the 3 would you normally get gas compounds? Okay, pause, answer the question, and then unpause, and I'll give you the answers in just a moment. Okay, right. 5 gas elements at room temperature. Make sure I've got the pen setting on. Pen. Right. First one, nice and simple. Hydrogen, number 1 on the periodic table. Number 2, helium. Other gas elements, we could have oxygen, you know about that, and nitrogen is gas. And you could have any of the other noble gases that go along with helium, so neon or xenon, or loads of them. 4 gas compounds at room temperature. So probably the most common one is CO2. That's the one you know. You could also have the less good CO, carbon monoxide. Oh, someone's at the door.
Are you making a video?
Talking about that. And other gases are so things like nitrous oxide, little silver canisters you see lying around in parks and at the edge of the road, NOx. And what else? You could have a horrible pollutant called sulfur dioxide, SO2. What are the 3 types of bonding? The 3 types of bonding are, that you have been taught about, ionic, covalent, and metallic. And what types of bonding do you normally get with gas compounds? So carbon monoxide, carbon dioxide, nitrogen dioxide, and sulfur dioxide. The sulfur and the oxygen, the nitrogen and the oxygen, the carbon and the oxygen, and the oxygen and the oxygen and the carbon and the oxygen are all bonded covalently. They're all covalently bonded. You know it's covalent because they're all non-metals. Covalent bonding happens when you have non-metals. If you have a metal and a non-metal, that's ionic. If you have just metals, it's metallic. These are non-metals, so you know you've got covalent bonding. There's going to be loads of information in this one, so sit back and relax, and I'll just read to you. Are you sitting comfortably? Splendid, I shall begin. Why is the Earth's atmosphere important, you ask? Well, the Earth is different to other planets in our solar system because it has an atmosphere that can support life. The atmosphere is an envelope of different gases surrounding the Earth. Here we have examples. The troposphere, 0 to 15 kilometers up, that's where we live, and aeroplanes fly. Next up is the stratosphere, 55 kilometers. In fact, it's broken down into many more subtle layers, but you don't need to know that level of detail right now. 80% of the atmospheric gases are 15 kilometers closest to Earth. This is a very thin layer compared to the diameter, which is 12,756 kilometers. So the Earth is 12,756 kilometers wide. The atmosphere is just 15 kilometers thick. So a very tiny proportion of the width of the Earth is the atmosphere above it. It's just a small, thin layer around the outside relative to the size of the Earth. And although it goes up quite high, hundreds of kilometers, most of it is in those first 15 kilometers. So what are the gases in the atmosphere? Go on, guess. You know one. Obviously, you know the most important one, which is oxygen. The oxygen is the air that we breathe. You also know that there's one of them is carbon dioxide, but actually the biggest gas in our atmosphere, as in the most abundant, the one that there is the most of, is nitrogen. 78% of the gas in our atmosphere is nitrogen. That's quite a lot. 21% is oxygen, the stuff that we breathe. So we breathe in 78% nitrogen and 21% oxygen. So only 21% of it is oxygen. When we breathe it out, it might go down to 16% oxygen. We only use a small amount. The remaining 1% is made up of things like argon, mostly argon, some carbon dioxide, and things like water vapor, so steam and clouds and stuff. 0.035% is carbon dioxide. Actually, it's probably more now due to climate, global warming, and the greenhouse gases building up. But a tiny, tiny amount is carbon dioxide compared to the others. It's quite handy that most of it's nitrogen. If it was 100% nitrogen, everything would 100% oxygen, everything would be like on fire. So 21%, good happy balance. So there we go. Here is a question. What type of bonding do these gases show? Oxygen, O2, nitrogen, N2, argon, Ar, carbon dioxide, CO2, and other gases like water vapor, H2O. What type of bondings do those gases show? We did the bondings in the starter. Pause. Have a go answering the question. Ooh, why does it explain their gases? The bonding is covalent. We talked about that. They're all non-metal, so it has to be covalent bond. Covalent bonds are incredibly strong, but there isn't much of a force of bonds between molecules. So, for example, the bonds in the H2O between the O and the two H's, one and the two and the two, the bonds between those two is incredibly strong. They're really held on tight. But the bonds between one H2O molecule and another H2O molecule aren't strong at all. So those can move away. And if molecules can move away from each other, well, you're just describing a gas, aren't you? So these moving away molecules basically means we have a gas at room temperature. Not always for water, obviously, but that was the example. The Earth's composition of the air has been roughly the same for nearly 200 million years, but the amounts of gases have changed over time. So let's go about 3,500 million years ago. The Earth would be very similar to the atmosphere on Mars today. It would have contained large quantities of carbon dioxide, but not much oxygen or nitrogen. What theories are used to explain how the Earth's atmosphere changed? Let's look at them. So let's just look at those numbers to start with. If we look at Earth, so currently it says Earth, carbon dioxide. Sorry, we've got 78% nitrogen. Nitrogen is blue. It's nitrogen in blue. Oxygen is orange, and carbon dioxide is green. Earth, 78% nitrogen, 21% oxygen. Venus, nearly all of its gases are carbon dioxide, 97%, and 3% for nitrogen. Carbon dioxide, again, in Mars is 95.3%, or only just below 3% for nitrogen, no oxygen. So, can you answer the questions? Which gas does Earth not have much of compared to the other planets? Look at those three. Which gas does Earth not have much of compared to the other planets? What living things use this gas up? Explain how. So, what gas? The answer to the first one is a gas. And then who uses those gas? What uses that gas? What gas does Earth have, but the other planets do not have? And what living things produce this gas on Earth? Can you explain? I'll pause and let you answer those questions. Done? Obviously, the gas that we don't have much of compared to the others is carbon dioxide. What things use carbon dioxide? Well, plants use carbon dioxide. They use carbon dioxide when they're photosynthesizing. They use it in the process of photosynthesis. What gas does Earth have but other planets don't? We have oxygen. How do we get oxygen? through photosynthesis. It's all about the plants. Right now, plants do the thing that we need most. They take the carbon dioxide out of the air and they turn it into oxygen. Photosynthesis is the process. Carbon dioxide in the air is taken, oxygen is given back. That is exactly what we need. Let's look at the history. So the Earth is around 4.5 billion years old. 4,500 million. Let's add to that. 4,500 million is found here. Yeah. So 3 billion is 3,000 million. Just to kind of give you a bit of history. And right at the beginning, Earth, like the others, had a lot of carbon dioxide. A lot of carbon dioxide. A little bit of methane, a little bit of ammonia, not much else. Then, 2 billion years-ish later, the carbon dioxide levels have gone down, the nitrogen levels have gone up. Some oxygen is around. About what we got today. Nowadays, almost all of the carbon dioxide is gone, has been taken in. A lot of nitrogen exists, and the oxygen are at the levels that we know, and it helps us live. So it's changed dramatically. Almost all of the gases at the beginning of the Earth's atmosphere, 4,500 million years ago, 4.5 billion years ago, aren't there. The gases that don't really exist are there. So there has been a change. Actually, there'll be a video linked into this that shows you this history. I'll show you a different example now. Okay, we can just follow some clicks. So 4,500 million years ago is how old the Earth is. When the Earth was formed, hydrogen and helium were the main gases in the atmosphere. These gases are very light and could have floated off into space, just like helium balloons. About 3,500 million years ago, 3.5 billion years ago, volcanoes did something. Volcanoes erupted. When they erupted, they released carbon dioxide and water vapor, so steam, and things like methane and ammonia into the atmosphere. When you fill the atmosphere with carbon dioxide and water vapor, because it came from volcanoes erupted and they took things from the core of the Earth, threw them up into the atmosphere. About 3.5 billion years ago, life occurred. That's a long time. 3.5 billion years ago. A long time. They occurred because the water cooled down. So it took like 500 million years to cool down. The water cooled down and formed what we know as the oceans. And in those oceans, there were lots of minerals and life occurred. Process of sort of 2.5 billion years, from 3 billion years to 500 million years ago, we end up getting things like plants. And when plants come along, green plants, more importantly, plants can do photosynthesis. So they take that carbon dioxide from the atmosphere, which was put there due to volcanoes. They take the carbon dioxide and they convert it into oxygen, which makes it all the more livable now. And then, boop, and now we have the kind of modern atmosphere. Oxygen reacted with ammonia to form nitrogen and water. The composition of the Earth has remained almost the same for 200 million years. Unfortunately, humans are ruining everything. Human actions are changing the balances of gases in the atmosphere. For 200 million years, everything's been fine, and then humans start burning fossil fuels. They release carbon dioxide and other pollutants in the air. How might this affect the environment, the atmosphere, now and in the future? We'll do that in another lesson. So, I stole this from my worksheet. So basically, we've got the first box is this box. This is box number one. Whoop. Number one. And then we've got 2, 3, 4, 5, 6, 7, 8. We've got 8 other boxes. This is box number 8. What you need to do is write down box number 1 and then work out what are the next boxes, next 6 boxes in order. And then box number 8 is the last. So we have given you the first step. We have given you the last step. The other steps are not in the correct order. Can you work out what the correct order should be and then write them down? It's quite a lot of writing, but you haven't had to do anything yet, really, so far. So the first task is for you to write these down in the correct order. I will give you the answers in the next lesson. So pause and correctly write down the order of the atmosphere. Go. You done? Splendid. Let's just check your knowledge. 3 questions. Write down the answers. Just the answers. You don't have to write lots because you've just done lots of writing. How old is the Earth? What are the current top 3 gases in our atmosphere? Not like your favourite, but the ones that there is the most of. Which gas has changed the most over the timeline of the Earth's atmosphere? What caused this gas to decrease so much? What is the main gas released by a volcano? Once you've answered the questions, move on. Another question. The pie chart shows the composition of the Earth's atmosphere today. We have different gases, A, B, C, and D. Can you work out what those different gases should be? Label A, B, C, and D. So just write A is, C is, B is, and D is. You done? Now we know those gases. This is a pie chart for the composition of the early atmosphere. This is going back. Maybe you have to flip back early in the lesson. Work out the gases and then higher level stuff. Can you work out what the formula for those gases are? If one of those gases is carbon dioxide, the formula is CO2. There we go. I've given you one. What else can you work out? Okay, you've done some questions. I'm just going to give you a bit of information and then one more set of questions and then we're done. Again, got a lot, so sit back and relax. Carbon locked into rocks. One of the other things that we talked about is how carbon dioxide was taken in by plants. But plants don't live forever. And when they die, surely the carbon dioxide should be released. No, not all of it. Other processes occur. Plants take in carbon dioxide and convert it to glucose and oxygen during photosynthesis. When animals eat the plants, some of this carbon can be transferred to the animal tissues, including their skeletons and shells. Over millions of years, the skeletons and shells of these organisms build up at the bottom of the oceans. They become covered in layers of fine sediment. Under the pressure caused by being buried by all these layers of sediment, eventually the deposits form sedimentary carbonate rocks, such as limestone, a rock containing mainly calcium carbonate. The formula for calcium carbonate is CaCO3. Some of the remains of ancient living things, animals and plants, were crushed by large-scale movements of the Earth and were heated within the Earth's crust for over a long period of time. They formed the fossil fuels, coal, crude oil, and natural gas. So the atmosphere, carbon taken in by plants and animals, and then over time turned into fossil fuels. Coal is classed as a sedimentary rock and was formed from thick deposits of plant material, such as ancient trees and ferns. When the plants died in swamps, they were buried in the absence of oxygen and compressed over millions of years. Crude oil and natural gas were formed from the remains of plankton deposited in mud on the seabed. These remains were covered in sediment and became layers of rock when compressed over a million years. Crude oil and natural gas is found trapped beneath these layers of rocks. Carbon dioxide gas was also removed from the early atmosphere by dissolving it into the oceans. It reacted and fell into the seabed as sediments and helped to form more carbonate rocks. So over the past 200 million years, the level of carbon dioxide in the atmosphere has not changed much. This is due to the natural cycle of carbon, which moves carbon between the oceans, the rocks, and the atmosphere. So lots of different ways of carbon has been taken in and then stored into the earth by rocks and fossils and other processes. All of these very important. So, last part. Let's answer some questions relating to it. Identify the process by which plants take in carbon dioxide. One word answer. Name the substance carbon dioxide is converted to in this process. Give a plant carbon dioxide. What does it give you back? When animals eat plants, the carbon is transferred into animal tissue, including their skeletons and shells. Explain how skeletons and shells end up trapped in sedimentary rocks. How does that become into a rock? When acid is added to marble rock, bubbles of carbon dioxide appear more slowly than when acid is added to chalk or limestone. Can you explain why? That's it. I'll make sure this PowerPoint is with you, so if you need to go back to help you answer the questions, that's fine. And also, there's a video that I've linked to make sure you watch that give you an extra level of detail about the history of the atmosphere. Okay, on to the questions. Send the work to your teacher. I believe in you. I know you can do it. Love you. Bye.